When we talk about continuity, if we have a graph of the function, it's usually immediately obvious when there's a discontinuity or not. If we can draw it in one pen stroke, then we're good to go. That would be continuous. However, if we have a formula, then it's a lot more challenging to figure out just from the x's and y's in our expression whether we have a function that's continuous or not. So you have to be a little more thoughtful. As an example, take a look at the function y equals sine of x over x. Where would that function be continuous? Here we're going to use the typical short form for handwriting continuous function here. It will be continuous, well, everywhere that this function is well behaved, because sine of x is continuous and x is continuous by itself. And if we take a ratio of those, we expect that by and large we're going to get the same properties in that ratio. The only problem spot is when we end up doing something mathematically implausible, like dividing by 0. So I would be worried about a discontinuity. And I'll put a question mark there because we don't know for sure, but at x equals 0 because of the divide by 0. We should investigate a little more thoroughly, but definitely something not so good is happening at that point. That would leave us with any positive x values being okay. We can put positive numbers into these two functions, and as we go along, we're going to get adjacent or nearby functions, function values, and likewise x less than 0. That's going to be fine too. The only problem spot seems to be because of the dividing by 0. Now, let's see if a sketch will help us with this. We'll see that it doesn't solve all of our problems, but at least it gives us some tool to start analyzing this formula-based problem. And what we're going to do is simply take some values of x and y over the interval -1 to 1. Now it's important to remember that we're going to be using radians in this class. Whenever we have a trig function, our default for sine, cosine, and tangent will be radians. So make sure you know how to set that in your calculator. At the point x equals -1, you're going to find that sine of -1 over -1 ends up giving you a positive value and approximately 0.841. So if we add a vertical scale on here, we're up towards 1 already. We know that 0 is a problem spot, so we won't go straight to that. Let's build up our values sneaking up on there. So at -0.5, -0.25. If you use your calculator, you'll find that these values end up being 0.96, and here you end up with 0.98, actually rounded 0.99. And if we go even closer, let's go to -0.1, we get 0.998. Well, plotting those points, we see very quickly we're pretty close to 1. And if we connect them into a graph, we would expect to see this kind of shape going forward. If we jump a little bit and go to positive 0.1, turns out the signs are going to cancel. We're going to end up at exactly the same value we had on the left of 0 at 0.998. And if we continue down, we're going to get the same values back again, just in the positive sphere. So we'll have a perfectly symmetric function here that looks like this. But where does that leave us at x equals 0? Well, the best way to do that is to plug in the values and see what we get. And that is going to be 0 over 0, and that is definitely undefined. I can't do any calculation with 0 and get a real number back, and so we would have to say our y value is undefined there. Graphically, we usually indicate that with an open circle at the location of the discontinuity, which is now what we have in our graph. This graph is fine and well behaved as we approach 0, but then it just sort of disappears for an instant and then continues on afterwards. It can't be drawn in one pen stroke because we'd have to lift our pen to get over this gap and then back down the other side. So from the graphical analysis, we can tell that sine of x over x is not continuous, but we had to get to the graph to really tell that for sure and see what was happening. With all that said, we can say something a little more detailed about the point x equals 0, and that's what we're going to look at next. In particular, we can ask the question, what does the value y approach as x approaches 0? So as we get closer to 0, as we sneak in here, where would we end up on the graph? In other words, where should we put that empty circle? And from our intuition, combined with the table of values that we generated for our graph, we would say that y approaches 1 as x approaches 0. In other words, if we got closer to x on this side as well, it looks like we would end up at 1 if it wasn't a hole in the graph. For those who have done calculus before, there is a really nice way to state this mathematically that you should be familiar with. If we talk about sine of x over x approaching 1, sometimes it's written like this, as x approaches 0. That's not really the technical way to say it, though. The way that we'd more explicitly say it is sine x over x in the limit as x approaches 0. So this whole framework here is actually equal to 1. So that's answering the question, if I were to sneak up on x equals 0, what value would I end up at in the end if I got as close to x equals 0 as I liked? I would be getting closer and closer to a value of y equals 1. And so that phrasing and this notation is what we're going to use moving forward.